Hello everyone. Today we are going to be discussing the advancements in research regarding metamaterials and their place in civil engineering practices. By definition, metamaterials consist of artificial, multi-purpose materials engineered to satisfy prescribed requirements. In other words, they are materials that have been artificially fabricated from submaterials to possess certain properties that are not found in nature. What is special about metamaterials is that they will not possess the qualities of the submaterials that create their skeleton, but will possess a completely new set of properties that can be manipulated based on design specifications. These properties are derived from the combination of their counterparts and not from the base materials themselves. The first attempt at an artificial material is said to have been performed in the late 1800s by Jagadish Chandra Bose. He performed experiments with the effect twisted structures had on microwaves. 50 years later, a scientist by the last name Koch managed to tailor a refractive index of a medium by arranging different conducting geometric shapes within the host. Since that period, the advancements in synthesis and novel fabrication techniques have given life to creation of composite materials that either mimic known properties or exhibit completely new and unnatural properties. For the purpose of this class and presentation, we will be covering metamaterials and their advancements in auxetics, wave manipulation within sound and thermal uses, along with new advancements in research on pentamodes and shape-changing materials. Let's begin with auxetic materials. Auxetic materials are materials that have a negative Poisson's ratio. These materials show this characteristic by expanding laterally when loaded in tension or shrinking when in compression. Most auxetic materials have a collapsible honeycomb structure which folds or expands when loaded axially. Honeycomb-structured auxetics are also known to have low shear moduli and are capable of handling higher shear stresses than standard materials. These materials have many applications, including composite material reinforcement, fibers, fabrics, and filters. Auxetic fibers are single or multi-filament structures that can be woven and continue to display auxetic properties. The properties for auxetic fibers can be tuned by changing the dimensions of the auxetic unit cell of the material or by pre-stressing the auxetic fiber before use. There are many applications for auxetic fibers, including clothing, fabrics, composite material reinforcement, personal protective equipment, seals, and filters. A great example of the application of auxetic fibers is for medicine-impregnated bandages. These bandages would have a small dosage of medicine, such as an anti-swelling agent, placed in the pores of the auxetic fiber. As the injury swells, the bandage would expand, releasing the medicine as the pores of the auxetic open up. Once the swelling has receded, the bandage would retract and the auxetic pores would close, stopping the release of the medicine. Auxetic materials are used in composite material reinforcement when a pliable and strong material is required. Auxetics as reinforcement generally take the form of fibers, as they are easier to work with. Auxetic reinforcements in composite materials improve the energy absorption, indent deformation resistance, and impact resistance of the base material. These reinforcements are also resistant to fiber pullout from the matrix material due to their ability to complement the deformation of that matrix. Auxetic reinforcements are primarily used in fabrics, ropes, and larger fibers. Auxetic fabrics can be a single or composite material with good energy absorption and material memory. The applications of auxetic fabrics include protective equipment, upholstery fabrics, clothing, and medical bandages. One company which focuses on auxetic fabrics is Advanced Fabric Technologies, which has developed an auxetic blast curtain which absorbs peak pressure from blast waves and catches shrapnel from those blasts. These blast curtains are able to absorb the peak pressure from a blast and catch any shrapnel without failure. The particular model shown here, produced by Advanced Fabric Technologies, has been tested for 40 psi blast waves, which it reduces to 4 after passing through the curtain. These curtains are able to withstand multiple blasts without showing wear, as opposed to conventional curtains that show wear after the first blast. Auxetic filters can be both foam and woven fabric filters. Auxetics reduce filter fouling and contain the ability to tune effective filter pore size. The auxetic's ability to expand in both directions when loaded axially allows for this tuning of the effective pore size. By changing the tensile load, one can create a specific pore size for the need. A patent for an auxetic-based filtering face mask has been filed in the US already. Next, we are going to cover wave manipulation capabilities of metamaterials, including sound and thermal manipulation. Some metamaterials can be used to manipulate sound waves. There are two methods of achieving this. The first is to use metamaterials which can absorb certain frequencies of sound waves to cancel out noise. The second method of controlling sound waves, which is unique to metamaterials, is to redirect them. This method uses the unique properties of certain metamaterials to redirect sound waves with minimal absorption. This method focuses sound and can be used to improve the acoustics of concert and lecture halls, ballrooms, and theaters. Metamaterials are required for this as they are able to interact with sound waves without dampening them, unlike ordinary materials. These materials can even manipulate sound waves with low enough absorption that even sonar systems can be deceived. The thermal properties of metamaterials can be divided into two categories: insulators, which decrease heat transfer, and heat sinks, which increase heat transfer. Thermal insulators are materials that reduce the rate of heat transfer. This allows for a specific area to be heated or cooled without adjusting the temperature of the surrounding area. Although many materials can and have been used for insulation, metamaterials have a lower rate of heat transfer and, unlike most insulators, are solid sheets which require less volume. Heat sinks are devices which are used to transfer excess heat out of a system. These devices are commonly used on small and large scale without metamaterials. However, metamaterials can improve their performance. In civil engineering, heat sinks are used for severe conditions. One example of where these metamaterial-based heat sinks could be used is in Alaskan roads. The severe freeze-thaw cycles have damaged the foundations of these roads for the last 50 years. One proposed solution is to run coolant pipes through the base of the road to reduce the severity of these cycles. However, this is very expensive. Using metamaterials, the freeze-thaw could be reduced while maintaining the structural integrity of the base. Finally, we are going to cover some new and progressive research being done to advance metamaterial technology. The first advancement we would like to cover is in pentamode materials. A pentamode is a material in solid state but that behaves similar to a liquid, hence the name metafluid. With a finite bulk modulus and vanishing shear modulus, the material resists compression forces yet can be easily deformed. These materials were proven to be theoretically possible in 1995, however the fabrication had not been successful until 2012 by Professor Martin Wagner. The most prominent proposed use of these materials is in transformation acoustics, theoretically creating the ability to cloak an object by deflecting or redirecting acoustic waves using specifically designed parameters in the pentamode material. The second progressive research area that we want to cover involves shape-changing materials. Shape-changing materials are materials that change their shape based upon external loads, such as a change in temperature, voltage, or loading. These materials have properties which change based upon what form they are currently in. Common shape-changing metamaterials start as thin sheets of material. Paper is a good example of a macroscopic shape-changing material, and graphene is a microscopic shape-changing material. Most shape-changing material designs were inspired by the Japanese paper arts of origami, to fold, and kirigami, to cut. Over the course of this presentation, we covered what metamaterials are and what they are being used for or researched for. Many metamaterials are already being used in practice, like the heat sink, or in the case of auxetic materials. In other cases, like pentamode materials, the research is so recent that the results have not entered the practical domain quite yet. However, the recent advancements in the fabrication technology has rendered the initially theoretical class of material to be a very promising advancement in material science and engineering. Throughout our research, it became clear that the possibilities these materials possess are numerous, and that the artificially engineered parameters present in metamaterials allow for them to be specifically created and designed to each individual practical use. We hope you enjoyed our presentation. We will take any questions you may have now. Thank you.